there was a dropout with him.
I see. So maybe I just start. Okay. Anyway, I want to thank Georg and other organizers to invite me to give this talk. Today, I want to share some of my recent work about this physics-informed data-driven algorithm for ensemble forecast of complex turbulent systems. And this is a joint work with Professor PIDD-CG from Purdue University. So this is the outline of this talk. So first, I will give a very quick introduction about complex turbulent systems and ensemble forecast, just to provide some basic background. And then I will focus on this new ensemble forecast algorithm. And I will first give an overview about it. Then I will show the step-by-step description. And finally, we all know when we want to do forecast, we have to do the initialization. So we'll discuss a few technical details about the forecast initialization. And after that, I will show the numerical test. I don't know if I have time, but if time permits, I will show the comparison of this new algorithm and the traditional Monte Carlo simulation. So first, some very quick introduction about complex nonlinear systems. And actually, these complex nonlinear systems appear in a lot of areas, such as climate science, geophysics, and material science engineering. They have a few typical features. So first, these systems often have strong nonlinear interactions, and they have these multiscale structures. And when we try to solve these systems, usually it is a big challenge because these systems usually have very high dimensions. I mean the high dimensional of the phase space. These systems are famous because they are chaotic and turbulent, so prediction will also be very challenged. They have a lot of intermittency and extreme events. And if you want to look at the statistics of these systems, then you will find that the distribution of those systems will not be Gaussian in general, but instead they have a lot of non-Gaussian features with fat tails. I show here a few very classical systems. Say, for example, this one, it's from a two-layer QG equation, and you can see a lot of large and small scale features. And overall, the system is pretty chaotic or turbulent. And if you're familiar with the famous Run 63 system, it is maybe the simplest and the earliest possible chaotic system. And it is famous because if you have a very small perturbation of the initial condition, then after a certain time, the solution can be divergent because of this chaotic nature. And this is another example which shows the time series of the El Nino South Oscillation, which is a very important climate phenomena in the equatorial Pacific. And in this red curve, which is a Nino's 3 index, you can see a few of these big events. And they correspond to the so-called super El Nino, meaning that they contribute a lot to our climate system. And when you show the probability density function, or PDF, then you can easily see this red one. It is not Gaussian, but instead it is skewed with a one-side fat tail here. So regarding these systems, we care a lot about their mathematical properties and the practical implementation. Two important tasks I care a lot about are the following. So first, because these systems are very complicated and high dimensional, we often try to develop some reducible models. And here I want to emphasize this statistical reducible model because these systems are chaotic. So usually if you focus on a single trajectory, it doesn't make too much sense. So we would rather try to build these statistical reducible models and try to capture some statistical features. And related to this statistical reducible model, we also care about the ensemble forecast of the systems. So forecast, of course, is important. And here again, I want to emphasize this word ensemble because of the same reason, that is, when we consider chaotic or turbulent systems, single trajectory doesn't make too much sense. And what we care about is the forecast of not just the mean state, but also the confidence interval or the entire non-Gaussian statistics. So we really need these ensembles to give us like the range of our forecast. And for this ensemble forecast, it is the most widely used method for predicting chaotic or turbulent systems. And the basic idea is very simple. So it is a probabilistic description of the model state using a simple or straightforward Monte Carlo simulation. And what we need to do is we start from some initial distribution. We draw samples here, and each sample is one Monte Carlo point. Then you repeatedly run the model forward, starting from different initial values we draw from this initial distribution. And at some time instant, you collect all these ensemble members, and you use them to construct a PDF. And this PDF is our forecast ensemble distribution. And the good thing is, such kind of ensemble forecast will provide us an indication of the distribution of possible future states by tracking the time evolution of this PDF. And these PDF are obtained by these ensemble members. So in this case, of course, it is one-dimensional, so everything is straightforward and clear. However, in high-dimensional systems, we have this famous computational challenge, which is called the curse of dimensionality. And that is, if we want to accurately predict this distribution or even try to formulate this distribution, we require an exponentially increase of the number of samples. And also we know if the dimension of the system is very large, then each run can be very computationally expensive. So essentially, we cannot predict the high dimensional system very accurately. This is what I just said. In practice, only a small number of ensemble members is affordable, as we all well know here. So the ensemble forecast based on this direct Monte Carlo simulation can provide reasonably accurate ensemble mean forecast, and that is actually typically people try to focus on in practice. And possibly the variance can be reasonably be accurately captured, but usually even the variance is not an easy task to recover. And then for high order moments like the skewness and kurtosis or the entire non-Gaussian fat tail distributions, these things are very difficult to capture using the classical Monte Carlo simulation. And also we need to keep in mind that forecast itself is important. However, before we do the forecast, we have to do the initialization of the ensemble forecast. Then we have to do data assimilation. Otherwise, we do not have initial values. And in practical situations, usually we only have partial observations, which means we have the observations for some state variables, which are noisy, but we also need to recover those state variables which are not observed. So that's why data assimilation is required. And again, in practice, we usually use Monte Carlo simulation for the ensemble data assimilation. Then again, we can only afford a small number of ensemble members for data assimilation. So for both forecast and initialization, this curse of dimensionality will bother us a lot. And in this talk, I will try to discuss an alternative to overcome, at least partially overcome these difficulties. So now I want to introduce this new physics-informed data-driven conditional Gaussian forecast algorithm. And keep in mind, we have two tasks. So here we have two goals. The first goal is we try to efficiently and accurately forecast the key non-Gaussian distributions, at least for a wide class of high-dimensional turbulent systems, using only a small number of ensemble members. So we try to do some work to overcome the curse of dimensionality. Also, in a lot of practical situations, the primary interest usually lies in the statistical forecast of only the leading a few large-scale modes. So that's why we also want to make use of this framework to develop some statistical reduced-order models which focus on only the leading a few modes. Then forecasting them will become much easier. So before I show the details or even the overview of the method, I want to show a very simple and general idea of what I try to present here. So there are three panels here, you can see. The top one is Monte Carlo simulation. So basically the background contour is a two-dimensional distribution, which is a simple example here for U and V. And these red dots are our Monte Carlo simulated points. So basically, based on these points, we can recover the distribution. We can either use delta function or use some kernel density estimation to make it smoother, right? So that's a new method I try to propose here, which called PIDD-CG algorithm, has two big steps. And the first step is, instead of doing Monte Carlo simulation for this original system, we try to do Monte Carlo simulation in a much lower dimension of the subspace. And of course, here I have only a two-dimensional system, so I can only say we try to do Monte Carlo simulation in one-dimensional here. I will discuss the details, but the idea is we don't do the Monte Carlo simulation for the high-dimensional system, but do it within only a subspace. Then the next step is to explore the so-called conditional Gaussian mixture structure. And what we want to do is, so here we have these low-dimensional samples. Then conditional on each of these samples, we can build a conditional Gaussian distribution. And then the final distribution will be made by using a mixture which consists of all these conditional Gaussian distributions. So you can think each of these conditional Gaussian distribution as one ensemble member, but these ensemble members are very different from the Monte Carlo points, which is just a point, but here it's a distribution. And by doing so, we only need to do the Monte Carlo simulation in a low-dimensional space, so we can kind of overcome the cursor dimensionality. Then I want to present this method into more detailed form. So it has these 5 steps. I will discuss more mathematical details afterwards, but the general idea is the following. So let's start with a high-dimensional complicated system. And the first step is to do some phase-space decomposition. And following the general idea on the left, what we will do is we decompose this entire phase space into 2 subspaces. And one subspace has low-dimensional features. And for this one, we will use Monte Carlo simulation or kernel density estimation to estimate the PDF. Then the remaining subspace will be high-dimensional. Then we will explore this conditional Gaussian mixture idea to do that. And when we try to deal with this low-dimensional subspace, we know that actually the state variable is fully coupled with those state variables in high-dimensional space. So what we have to do is we have to build a statistical closure approximation of the dynamics in this low-dimensional subspace, such that we can just run this low-dimensional equation and get at least some approximation of the PDF related to this low-dimensional space. And then, as I said here, conditional on each of these sampled points, we will build a conditional Gaussian mixture here. And essentially, the high-dimensional PDF will be decomposed into different conditional Gaussians, or you can think of them as Gaussians if you only look at the high-dimensional space. And then, instead of forecasting this high-dimensional subspace directly, what we want to do is we try to forecast the conditional mean and the conditional covariance instead. And the nice thing of this framework is that we can actually write down the closed analytical formula of the time evolution of this conditional mean and the conditional covariance. So this closed analytical formula will facilitate our calculation because we are no longer needing the Monte Carlo simulations. So I don't show the details, but everything on the right-hand side just depends on the original system, which can be written down analytically. This is a very nice feature. However, still, if the system is very complicated, the right-hand side can be complicated as well. So what we do as the last step is we still keep the basic dynamics of these moment equations, but we replace the complicated nonlinear interactions in the moment equation by some much cheaper recurrent neural network. And using this neural network, we can compute these moment equations in a much more efficient way. And note that when here the target is these moments, the mean and the covariance. So we need to be very careful in designing this neural network. And here we use an information criteria as a loss function because the information criteria allows us to compute the difference between the 2 PDFs. One is the truth, one is the one that corresponds to the neural network. And these PDFs can eventually be made by these moments. So that's why when we forecast moments, it's better to use information criteria than the traditional L2 norm as a loss function. So now I want to discuss more technical details about this method. So just following this general overview graph, I will divide this entire picture into 5 steps. First, the phase-space decomposition. So let's just start with the general formulation of turbulent systems, at least in fluids. So we treat this U as a state variable. So on the right-hand side, first we'll have these linear terms, the damping, dissipation, and other linear interactions. This BUU is a quadratic nonlinearity, which usually conserves energy, like the advection or other things. This F is a deterministic forcing, and we can add some stochastic forcing if we want. So now what we do is we can at least formulate and decompose this U into X and Y, where this X is a low-dimensional subspace. And physically, usually it corresponds to a collection of larger scale modes, while this Y is a remaining high-dimensional subspace, and it contains those smaller scale modes. And of course, how to choose X and Y, this is kind of dependent on the problem we care about. And the one feature we need to notice that is, for this quadratic nonlinearity, it of course involves Bxx, Bxy, and Byy, right? And since Y is those smaller scale modes, so this Byy often involve high frequencies, or at least it looks more noisy than Bxx and Bxy. And what we can do is we can try to effectively parameterize this quadratic nonlinearity for these interactions between Y and itself, or we can do some systematic approximations by closures. So why we need this step? Because with this step, then this original system will have a very clear formula here. Because we now try to replace Byy, so what remains will be all the nonlinearity of X itself, the linear term of Y, and the nonlinearity between X and Y, right? So we don't have Y square or Byy, those terms here. So this system may look still similar to this one, but this new system, system 2, has some very nice features. And in fact, one design feature of this system is that given one realization of the time series X within an interval, then the conditional distribution of this Y conditional on this given X is a Gaussian distribution. And this can be seen in the following way. So if X is given, then everything on the right-hand side with blue colors are null, right? Including these nonlinear terms and including these noise coefficients. So in terms of this Y itself, it's a linear system. So that's why the distribution is Gaussian, because once all these blue terms are given, then the dynamics is linear, the noise is given. So it's kind of a linear Gaussian system. And this distribution is conditional Gaussian, and the conditional mean, mu, and the conditional covariance R can actually be solved by a closed analytical formula, and the details I will show later. But this is one of the key features we will explore later when we try to build the conditional Gaussian mixtures. And with this closed analytical formula, we can solve these equations in a very efficient and accurate fashion. So I want to provide one remark here, because maybe you will say, hey, this system 2 can be very special, right? It may be very different from this equation 1, but I want to provide some evidence, which is many complex systems actually already fit into the framework of 2 without any approximations. So there are a lot of physics-constrained nonlinear stochastic models, such as all different kinds of Lorentz model, like Lorentz 63, 2-layer, Lorentz 96, Lorentz 84. Without any approximations, those systems already belong to this framework 2. And there are also other examples. And if you are familiar or interested in stochastic coupled reaction diffusion models in neuroscience or ecology, I can also provide you some examples, especially this physical Nigomo model. And for those multi-scale models in turbulence and geophysical flows, you can apply some Fourier decomposition or spectral decomposition to these systems. And then those systems will also belong to the general framework too. For example, the Bosniak model or Shallow-water equations. And what I want to show here actually indicates that the mathematical modeling framework, number 2, is an appropriate one to characterize or at least approximate many nonlinear and non-Gaussian systems in different areas. So now we want to discuss the second step, which is we want to focus on dealing with low-dimensional subspace. So first, because the dynamics of this low-dimensional subspace variable is fully coupled with y. So even if we want to forecast x, we have to run the entire coupled system, right? If we don't do anything to facilitate the calculation. So here, to reduce the high computational cost, we will build a systematic multi-scale statistical closure of x here. And how to do that? So first, we try to decompose this high-dimensional variable y as y1 and y2. And usually y1 is the resolved subscale process, and the y2 is the rest unresolved ones. Then correspondingly, we can denote mu1 and mu2 as a conditional mean of y1 and y2. So to rewrite the equation 2a, which is the equation of x, originally it was dx over dt equals a0, which is a function of x, plus a1, which is another function of x times y plus noise. Now we write it as, still we keep all the nonlinearity of this x here, a0, but we decompose y as y1 and y2. So we have a11 times y1 plus a12 times y2, just very simple manipulation. Now we can rewrite this y1 as its mean plus the fluctuation part. Right? So we keep this mean explicitly here, and we keep this noise. However, we put the fluctuation part of the resolved modes and the entire unresolved modes as this residual part. And this is a0 is a function of x, which is the largest scale variable. Mu1 is a conditional mean of the largest scale of the resolved subscale modes. So these are usually something we can resolve or observe. But this entire thing will be something that lies in a much faster time scale or something that is unresolved. So we treat that as fx, which is a closure we will build. Of course, the details here will be very complicated. So that's why we here propose to use a recurrent neural network to approximate this fx. And basically, since the equation here depends on x itself, mu1, which is a conditional mean of y1, so we treat x, mu1, and the fx itself as an input to predict the next step of fx. And by doing so, we can use a neural network to build this closure. And remember here, we do not touch y2 or the residual part of y1. So later you can see we can use this way to build a very simple closure reducible model, which contains only x and the leading a few modes of y, which is the y1. So that can give us a model reduction.
Can I ask a quick question?
Sure, please.
Why is it important to decompose y into a resolved and an unresolved
because
I mean, the same could go through if you just had y, right? If you
Yeah, I mean, the crudest approximation is to keep the entire y, but here we want to build a reducible model which not only contains the larger scale modes x, but also contains part of the unresolved modes, of the small scale modes. So you can, of course, choose this entire thing as your residual. You can completely ignore that, but here I want to make things a bit more delicate, basically.
Okay, thanks.
Yeah, that's a quick answer. Okay. Now we can use this way to forecast the PDF of x by running a much lower dimension system, which contains only x and y1. Or if we ignore y1, we can just run the x itself. And then because this x is by design a low dimension system, so we can use Monte Carlo simulation. Or if we want to do a smooth version, we can use kernel density estimation. And here we choose a Gaussian kernel. So which will be the simplest possible choice. Then we have done with the result with the larger scale part X. The next step is to deal with the small scale Y part here. Recall that in the previous step, we used the Monte Carlo simulation to get J samples of this X. Now what we want to do is conditional on each trajectory of this X from the previous Monte Carlo simulation, we can explore the structure of this model to solve the conditional distribution Y given each of these trajectory we got from the previous step. And as I mentioned previously, this conditional distribution is a conditional Gaussian distribution. And if you are familiar with data simulations, then you can view this as a posterior distribution of the analysis state Y given the observation X. So this is kind of a generalized version of the Kalman-Busse filter, but in a nonlinear way. Then with this step, what we can do is we can write down the joint distribution in the following way, which first contains the kernel density estimation of X. And remember, I said I use a Gaussian kernel for each ensemble member of the Monte Carlo simulation here. Then conditional on each Monte Carlo point, we have this conditional Gaussian distribution from the previous closed analytical formula related to data simulation. And there's one very important fact, that is the error bound of this joint distribution in terms of the number of sample points does not depend on the dimension of Y. It does depend on the dimension of X. So that means as long as this X stays in a relatively low dimensional subspace, it's sufficient to use just a small number of samples to accurately approximate this joint distribution. And in fact, this is a Gaussian, this is a conditional Gaussian, so their product will be a Gaussian. And this entire non-Gaussian joint distribution will be approximated by a Gaussian mixture at the very end. So we know Gaussian mixture can give us arbitrarily non-Gaussian features. So we use this way to recover the fat tails and other non-Gaussian features. And also I want to make a remark here, that is the physics-driven ingredient here is reflected in the data simulation step to solve this conditional distribution. Because when we try to solve this conditional distribution, we explored the mathematical structure of the equations of both X and Y. So when we try to write down the posterior distribution, we first do a forecast, then we do analysis. But everything can be solved analytically. And therefore, this conditional distribution will be very different from the straightforward kernel density estimation, which is purely data-driven, without using any dynamical information. So then step 4 is how to solve this conditional distribution, Py given Xj. And as I said, this equation, these two-moment equations can be written down using closed analytical formula. And just for the completeness of this step, I write down the details of this analytical formula. And this A0, A1, or capital A1, A0, and this B1, little case B2, they are just the right-hand side of the original equations. So once you know the original conditional Gaussian system, then you can write down the closed analytical formula of these moments. So everything should be known, although these terms can be pretty complicated. So at least this system can be solved using standard ODE solvers, Euler or Luger-Guter schemes. So we can avoid using Monte Carlo simulation to solve the conditional mean and conditional covariance, which can save us a lot in terms of a computational cost. Then the last step, as I said, is this equation still looks pretty complicated, especially this A or this B and this R, they are big matrices. So the operations, the number of operations for multiplications can still be a lot if we just solve these systems for high dimensional ones. So what we instead to do is we try to approximate these complicated nonlinear terms by a recurrent neural network. And we use the information criteria to train the loss function such that by approximating this part using neural network, we can still get accurate moments in terms of the mean and the covariance. And for the details, just recall what we needed in step 2, which was we want the statistics of this y1, that this is mu1 here, right? Then this is the residual part, as I mentioned. So for this moment equation, we can actually first write down d mu1 and the dr1, which are the posterior mean and the posterior covariance of this y1. Then for the right-hand side, we keep this basic dynamics, but we approximate these complicated nonlinear interactions by a function of g and a function of f. And both g and f are approximated by a neural network. And we compute the output from this entire equation. Then we get mu1 and r1. We use them to formulate the distribution. Then we use the information criteria to train these neural networks. And for this f and g, again, we only use the large scale variable x, the conditional mean and the covariance of y1 as our input. Of course, we have to use f and g themselves as input. So still the input will be consistent with the input of the closure part of x. So overall, we don't touch the y2. We only use x and some information of y1 as input. So this entire system will be a closed system in terms of x and y1.
Can I ask another question?
Of course.
Go one page back, please. So are you training on the difference between, let's say, d mu1 dt minus a naught plus a1 mu1? And that is how you train? So do you that's how you do it, yeah?
So that's a good point. So we approximate these two, G and F, by neural networks, right? Then we get output from F and G. We compute mu1 and r1. Then we use mu and r1 to recover the PDF. And so we directly train the PDF, difference between the PDFs.
Right, so you don't actually require the information of d mu1 dt. So you don't require that.
No, we only need the information for this F and G here.
Okay, so that means it probably it will work for noisy data as well then?
Yes, actually, the example I will show is for the noise data.
Okay, nice, thank you.
Yeah, thank you. Yeah, thanks for this question. Yeah. So actually here we can already see that because everything here only involves x and y1. So we can make use of this procedure to build a reducible model, statistical reducible model for x and y1 because we didn't touch y2. Of course, if the interest lies on the entire full system, then we can do a similar equation as this one, but we replace mu1 and r1 on the left-hand side by mu and r. And alternatively, here we also will include mu2 here. So if we are interested in the entire system, but usually we care about some low-dimensional phase space. So yeah, what remains is to train this neural network. And as I said, because our focus is on these moment equations, so it doesn't make too much sense to compute the L2 norm, because when you compute the L2 norm, you cannot even guarantee the positivity. The positive definite features of this covariance matrix. And sometimes you can get very weird result. So instead, we use this information criteria. So we train these neural networks, then we recover mu1 and r1. Then we use mu1 and r1 to formulate the PDF. And this information criteria is called the relative entropy or KL divergence. So the reference solution is the truth, and this PF is what we obtained from the neural network. Then we try to minimize this relative entropy to train the neural network. At this point, we discussed some details of this algorithm, but still there's one thing that is very important we haven't discussed yet, which is the initialization of the conditional statistics ensembles. So the initialization of this algorithm actually has two major differences compared with the traditional ensemble forecast using Monte Carlo or whatever. First, recall that what we use here as each ensemble member is not a single point, but instead a conditional Gaussian distribution. So initialization will be different. And also second, because we use neural network approximations for both the closure model of X and for the approximations of the moment equations. So how to do the initialization of this neural network will also be another important task. And especially if we go back here, we notice that when we use the neural network forecast, we actually lose the Markovian properties. We here need the information not just at the current time instant t, but we need to go back up to t minus m time instant. So this will be slightly different from the traditional ensemble forecast. But both issues can be easily solved. So first, for the initialization of the hidden variable y here, this is actually very straightforward and simple. So all the initial ensemble members of this y will take the values where this mu and r are the posterior mean and covariance are computed directly from the data assimilation formula of this entire system. So we just run data assimilation once for this original system, and we will get 1 mu and 1 r, and we use the same mu and the same r as the initialization of different conditional statistical ensemble members. But later, when we run the moment equations, these different ensemble members will be different. And the good thing about this is, actually, this initialization will be completely consistent with the traditional ensemble forecast algorithm, because all we did was to use direct or the classical data assimilation, except that we have closed analytical formula here. And now about the initialization of this f and g in the neural network. So here, what we need to use is just mu, r, and x. And x is the observations, which is simple. And for mu1 and r1, we just need to let the system run for a grace period. Then we get a time series of the past information of mu1 and r1. Then we plug them in this system, which is also not too difficult. The most challenging part is actually the closure model of the larger scale dynamics X, because now we not only need the past information of X and mu1, but also we need the information of this fx. And the terrible thing here is this fx requires the past information of the trajectory of y1 and y2, right? But the nice thing, again, for this kind of conditional Gaussian system is that we can do a smoothing procedure and a backward sampling, and both procedures can be written down using closed analytical formula. So just to complete this concept, so data assimilation, usually we refer to filtering, which is only a forward procedure. But if we have the information in future and want to get the state estimation in the past, we can do a backward pass, which is called smoothing. And here we use this smoothing and we add some noise. We can get a time series of sampled trajectory of y. And this sample trajectory will be used for the initialization of this fx. So now I discussed a lot of technical details, but I think the most important is to show you some results. Otherwise, it's difficult to understand how this method works. So the numerical simulation I want to show here is based on this topographic biotropic flow, which is one of the classical test examples in geophysics. And the reason we propose this one is this model actually contains a lot of very nice features, such as the multiscale interactions and the transport among the zonal flow and the fluctuations. And also when we look at statistics or the time series, this model will give us a lot of intermittency, non-Gaussian distributions, regime switch, and extreme events. So here we just use a spectral method, and we can write down the spectral formula of this layered topographic model. After we do this spectral decomposition, this larger scale variable u will be retained, and the q is the vorticity, because here string functions, they are related to each other. And the h here is a topographic effect, which is kind of a forcing. Beyond that, we also add a passive tracer here. So eventually we have a large scale zonal mean flow u, which goes from the west to east. And we have many fluctuation modes, bk. And we also have some passive tracer modes here. So this entire model is nonlinear because these coefficients, they depend on the larger scale modes. These coefficients, you can treat them as damping and oscillation frequencies. So overall, the system is fully coupled by nonlinear things. But if we are given this U here, then the dynamics of V and T, they are conditional linear and conditional Gaussian. So we basically skip the first step because this system already belongs to the conditional Gaussian framework. And as a test example here, we choose 10 different Fourier modes. So in total, we have 41 dimensions because we have real complex part. And only a realization of U is observed. Just want to mimic the realistic case, we observe the large scale features. And we have no observations of V and T here. And when we build the statistical correlation model, previously we said we have Y1 and Y2. Now Y1 only contains V1 and V2, and Y2 contains V3 to V10. So we want to see if we just keep two modes, how good we can approximate the larger scale features and how they will give us some feedback to the small scale or unresolved modes. And we test two dynamical regimes. One is called the strongly non-Gaussian regime because the statistics or the PDFs are highly non-Gaussian. Another is nearly Gaussian regime because of the Gaussian distributions. But no matter which regime, you can see a lot of chaotic behaviors. Like the first row here is the time series of U. And the second and third row are the time series of V1 and T1, the first Fourier modes for velocity and for the tracer. So this regime is highly non-Gaussian because you can see this regime switching behavior. Basically, you have very small amplitude for a while, then big amplitudes. So overall, your distribution has fat tails because of these big events, all these ones. While for this regime, you have slow and fast oscillations, but overall, the amplitude stays at the same level. So if you look at the statistics, then the PDF will be nearly Gaussian. And like for this regime, you can see clearly this regime switching behavior, right? If your U oscillates relatively slower, here V is relatively slower. Then if U is very negative, which means you have a westward jet, then you have much faster oscillations for V and T. And the last two panels here are the reconstructed physical field of the velocity and the tracer. You can see a lot of this intermittency and chaotic behavior. So first we want to look at how good we can do for predicting the large scale mean flow from the closure model and the conditional statistics using the closed formula plus neural network. And I show the results of both regimes. So for the strongly non-Gaussian regime, the large scale U can be predicted quite well up to the decomposition time. So here, what I showed, the lead time equals 1, which is about the decomposition time. And the V1 and the T1 also predicted pretty well. And this regime switching or the slow fast behaviors are overall accurately recovered. And for these statistics, they are okay, they are not perfect, but still in most of the time instance, they are pretty good. There are some places which are not perfect, but still acceptable. And for the nearly Gaussian regime, which is a much easier case, so we get everything basically almost 95 or 98% accurately. Then based on that, we can try to recover the entire non-Gaussian PDF. And for the purpose of comparison, we also show the results using Monte Carlo simulation. But the difference is that when we generate a truth based on Monte Carlo simulation, we use 50,000 samples, but in our algorithm, we only use 100. And here you can see the blue one is the result from the Monte Carlo simulation, while the red one is the result from our new method. For the presentation purpose, I can only show 1 or 2 dimensional, but we can actually compute the high dimensional statistics, which are also pretty accurately recovered. So this is a strongly non-Gaussian regime. You can see the fat tail here, which are especially here, which are pretty accurately recovered. And this weird behavior of highly non-Gaussian features are also accurately recovered. And note that we show both the transition state and the equilibrium state. So the method works not just for the statistical equilibrium, but also works when you start from a specific initial condition and just want to run forward for a short term. And similarly for this Gaussian regime, which is actually an even simpler case, and we get pretty accurate results. So then we have to ask ourselves a question, that is this information criteria to train the neural network a necessary step? What if we just use L2 norm as a training criteria? So here, when we use L2 norm as a training criteria, we enforce the covariance matrix to be positive definite. So we did a lot of tuning here. But still, even with these tunings, even if we don't suffer from this negative, non-positive definite covariance matrix, still the error of the forecast using the L2 norm for the training will grow much faster than the information criteria. And in the paper, we also show the training error, which shows that the L2 loss function will saturate at a certain level, which is still not as optimal as the information criteria. So finally, I think I still have some time. I want to give a final remark, which is how different is this conditional statistical ensemble members from the Monte Carlo simulations. And here I use an even simpler prototype nonlinear multiscale tried model, and will treat the first variable as the observer variable. So basically, the first few terms are linear terms, but there's a quadratic nonlinearity between U1 and U2, and feedback of minus U1 square. So this entire nonlinearity is energy conserved. And this is actually a very useful test model because it mimics features of at least the low frequency part of general circulation models, and it can create a lot of non-Gaussian distributions. And it was tested the scale for the use of the model for fluctuation dissipation theorem. I choose different dynamic regimes. The details are not important, but what's important is they have all these non-Gaussian features. And this is something we want to show for comparing this method and Monte Carlo simulations in terms of the sample points. So again, the background contours are the true distribution. And for this one, the red dots are the Monte Carlo simulations. I use 500 here. So basically, the true distribution can be recovered by Monte Carlo simulations pretty accurate here if we have a large enough samples. While the green ones here are the ensemble means of each conditional Gaussian ensemble members. And what you can see here is these ensemble means themselves will not recover the true distribution. But don't worry about it, because for each ensemble member here, we still have a covariance, which is around it. And this covariance will actually help us to recover the entire distribution. And in these two panels, we can see that the Poisson mean, especially here, they are concentrated in the middle, but the Poisson covariance it's much bigger than 0. So which means each ensemble member will cover a pretty big area. So that can recover this entire distribution. And for this case, it looks like for this two-dimensional case, these conditional ensemble members, they are concentrated in a one-dimensional manifold, right? So this is, to some sense, a hint that tells us we can overcome the cursor dimensionality, because here we only need to recover this one-dimensional subspace compared with the two-dimensional one. And similar for other cases, sometimes you do need a lot of samples if your noise is very low for some of the variables. But overall, you will have some behavior that is different from Monte Carlo simulations. Finally, for the summary, here we propose a physics-informed data-driven algorithm for ensemble forecasts of complex turbulent systems, and we only require a small number of ensemble members. And the method combines the ideas of statistical collusion model, data assimilation, conditional statistical ensembles, machine learning, and information theorem. So in addition to forecasting the entire PDF, this method also provides us a natural way of building a statistical result model, especially for X and Y work. So I guess I will stop here, and I want to say thank you very much for listening to this talk.
Thank you very much, Nan. That was a fantastic talk. Very, very interesting.
Thank you.
Are there questions?
Yeah, Nan, thank you. Can you maybe explain one thing for me? Mm-hmm. So I know with these sampling strategies, that you can talk about samples from a distribution in terms of delta functions. You approximate the PDF that way, and then everyone does it. You can approximate that by a KDE. But you said something very interesting, which is that you use a KDE and you still recover convergence to the correct PDF. Is there some kind of trick there? Do you take that the kernel width goes to 0 or something like that?
Let me try to see if I understand your questions completely. So, sorry. So I guess you ask about, so the method has two parts. For the X component, I did use KDEs, but for the Y component, I use the conditional Gaussian distributions. So you're asking X part or the Y part?
The X part.
X part, yeah. So X part, I use the traditional KDE algorithm. So here, because we use a relatively small number of ensemble members, so the bandwidth will not shrink to 0. But if you take the limit of infinitely many ensemble members, then the KDE method will converge to the traditional Monte Carlo simulations. And the bandwidth will shrink to 0.
Okay. Yeah. I always worry that when you talk about a KDE in some kind of space, even in the low dimensional X space, if really there's some kind of dynamical information so that something should lie on, like my samples should lie on some kind of manifold, then when you initialize the KDE, you sort of inflate incorrectly in some of these dimensions and you move off the manifold.
I believe here, of course, you have to assume you have ergodicity and maybe some other features. Otherwise, your samples can be concentrated, like you said, in a specific manifold, then you cannot cover the remaining subspace. In that case, I will worry about if the KDE will converge to Monte Carlo simulation. But in general, if you have a pretty nice feature of the system, for sure, you will have the convergence.
Okay, thanks. That's great.
Yeah, thank you for this question.
Any more questions? Maybe I can ask them, and could you please go to page 25? So at the top one, for the strongly non-Gaussian regime, it appears to be where you got the biggest errors is in this sort of in the laminar periods. Like if I look at the bottom two rows.
You mean here, right?
Yes.
Well, no, actually, I don't know if it's laminar or not, because these are the statistics.
Right.
You can only, I can only say like maybe in one regime, there will be big errors, and in another regime, there will be okay.
Yeah, but they're also, if I look at V1 and T1, it corresponds to the sort of more quiescent regions, right?
I see what you mean. Yeah. So
is this like, could you comment on it, on this, why it happens, just why you're doing so badly? Is it like an ensemble size error?
It could be like
you need
to inflate the
exactly.
noise. Something like that. Yes.
Yeah.
Yes. Yeah.
It seems like you're not corrected, right? You
right.
You trust your forecast or something, and then you're not corrected by them.
Yeah, I think this might be overcome by the noise inflation. I mean, covariance inflation, maybe. Yeah, but that's a good point. I should look at that. Yeah, I will look at that. Thank you.
Thanks. Yeah. And have you tried this on other systems? On data, where you're only given data and you have some. Is it possible to extend this to system where you're only given data and you have some kind of vague idea about some?
Yeah, I'm trying to look at the case in which we are given like a few time series from one system, but we don't know the exact system. Yeah. So we try to build some approximate models. Then we use this method to do the forecast. And we haven't done anything about that, but that's something we are planning to do.
Okay.
Eventually, we have to do some data-driven cases, right? If we know the perfect system, the case will be easier than the case with model error. And in fact, here the reason, actually, the original motivation here was just to do the forecast. But later we realized maybe building the reducible model, which contains a model error, will be a more practically useful task. So then we combine these two things together in this work.
Mm-hmm.
Yeah, but I completely agree with you, and it will be more interesting to look at the case with the real data plus some like partial knowledge of the underlying systems.
Yeah, it would be great to see. You combine so many different features. It would be nice to see them all working, together for just data-driven. I think.
Or which part
Very
fails.
Nice. Say again.
Or which part fails.
Yeah. Yeah.
That's a very good point.
Yeah. Are there more questions?
Well, so I know I zoomed out at some point because I was thinking about something else, but can you comment on the data requirements that your initialization of the model and the neural network actually requires for you to do the forecasting?
Very good point. So the initialization here is slightly different from the traditional ensemble forecast, because when you do the traditional ensemble forecast, you only need to do the data assimilation at the current time instant, right? Okay. So here, because this neural network requires some memories, like here we forecast t plus 1, but we need the information not just at t, but go back to t minus n. So we do need to run the model first for a grace period to get some data. Then we use the time series as the input of the neural network. And there are two different neural networks here. The first one here is simple. So we only need the past observational data X and the past information of this mu and R1, which are the target of our reducible model. So this part is easy, just need to run the model first forward for a short period. And the more difficult part is this one. So for this one, we not only need the past information of X and mu1, but we also need the past information of the entire unresolved modes. And what's worse here is, it's not just the mean, but actually the trajectory of all these modes. So that's why here we propose this backward sampling. And the good thing is, this backward sampling, which is based on the smoothing technique, can be written down using the exact closure formula. So each time when we do the initialization, we first run this equation backward up to t minus n, and we get some time series of this y. And this y will be the y1 and y2, both of them. Then from this sample trajectory, we plug them into this f to get the initialization of the neural network. So this is a crucial step. Otherwise, we cannot do the initialization of the closure of this X. So it does require some techniques, but the good thing is everything here, regardless of filtering or smoothing or backward sampling, they can all be written using closed analytical formula. So we don't need to worry about all those sampling issues, and we don't need to tune a lot of those covariance things. So that's why we, in the very first step, we said we want to approximate this system by these two. So with this equation 2, we have all the analytical expression for this data assimilation, for the forecast, for everything.
Yep.
And hope I at least partially answer your question.
Yeah, thank you very much.
Thanks.
Actually, on that note, the M, is that as well learned, or how do you determine it? Or do you determine it with a different method, like, optimal or something? The M, the time delay, the small.
Yeah, this is, currently we choose that empirically.
Yeah.
Like we choose that for 1D collision time for now. But I totally agree with you. There might be some optimization procedure behind it to find the best, best delay here.
Okay.
That's a good point.
Are there further questions? Well, let's thank Nan again for a great talk. So thanks very much.
Thank you, everyone.